So in the last part of the lecture, we learned that the likelihood is given by a multiplication of all the individual probabilities, which is fw of phi of xi to the power yi times 1 minus fw of phi of xi to the power 1 minus yi. So next we'll maximize the log likelihood. So that will give us a maximum likelihood estimate of the parameter w. Which is the same thing what we did in the previous in the last part of the previous lecture in linear regression. So we'll now maximize this likelihood to get the max likelihood estimate, which is known by w star. So w star simply equal to the arg max over w, the likelihood function w. So now let's maximize this likelihood function. So to maximize this, we compute its derivative and set to 0. So we can compute the derivative with respect to the parameters w of the likelihood function, which is phi of xi to the power yi times 1 minus f of phi of xi to the power 1 minus yi. So as we saw in the last lecture, instead of maximizing this likelihood directly, we can maximize the log of the likelihood. So the log of the likelihood would, so the derivative would then become of the log likelihood is so you're saying the log of this thing. So this is equal to yi times the log of fw phi of xi plus 1 minus yi times log of 1 minus f. Right. So we can take this derivative inside. So this becomes sum or I equal to 1 to n yi times the derivative of log of w phi of xi plus 1 minus yi times the derivative of this expression, which is log of 1 minus f. So this summation over this entire term is represented in a bracket. So we can ignore this bracket for the sake of make it look simpler. So this becomes sum or I equal to 1 to m yi over f of x phi of xi times the derivative of f of phi of xi. plus 1 minus yi over 1 minus f of phi of xi times the derivative of 1 minus f of xi. So again, the summation over the entire term, and write this entire thing in a bracket. So this becomes sum over all I equal to 1 to n yi over for phi of xi. So derivative of this one, the constant is 0, and we'll take the derivative with respect to this term. So this becomes 1 minus yi over 1 minus fw phi of xi times the derivative of f. Right. So as we had seen the property of the logistic function. So this is a logistic function of, this is g of phi of xi transpose times w, and we have seen that the derivative of g with respect to its argument is g of t times 1 minus g of t. So we'll use this property over here. So this becomes sum of I equal to 1 to n yi over f of phi of xi minus 1 minus yi over phi of xi times fw of phi of xi times 1 minus fw of phi of xi times the derivative of this argument phi of xi transpose w. So this simply becomes sum all I equal to 1 to n yi times f w, sorry, y times 1 minus fw of phi of xi times 1 minus yi times fw of phi of xi times the derivative of this is simply phi of xi. So this simply becomes yi minus yi times f of phi of xi times plus yi times f of phi of xi. Multiplied by phi of xi. Similar, so this term cancels this term. So we get the derivative as so this is the gradient of the log likelihood function, right? So we can simply write it as the gradient of the log likelihood function is simply sum all I equal to 1 to m yi minus f w of phi of xi times phi of xi. So this is the gradient of the function, and like in least squares, as we mentioned earlier as well, in least square we just directly set this gradient to 0, and we obtained a closed form solution for the parameters w, which was a very simple. So in case of linear regression, we got the solution as phi transpose phi inverse times phi transpose y. But for this particular expression, if we set it to 0 and try to compute the closed forms, we will find that we cannot compute a closed form solution for it, right? Because this function is not linear in its parameters w. This function is a logistic function which is non-linear in the parameters w. So as such, if we try to simply set it to 0, we wouldn't have closed form solution. So this doesn't give any closed form solution. So we'll use the gradient descent algorithm to finally compute the optimal parameters w. So the next part of the lecture will derive the update rule for the gradient descent using the gradient that we've computed for the log likelihood function. So as we have seen in the previous lecture, we computed the gradient of the log likelihood. The gradient of the log likelihood function with respect to the parameter w is sum all I equal to 1 to m yi minus f w of phi of xi times phi of xi, where fw of phi of xi is just a logistic function. So we can write simply as the gradient, the log likelihood function is sum all I equal to 1 to m yi minus 1 over 1 plus e to the power negative of phi of xi transpose times w times phi of xi. Right. So as we discussed in the previous lecture, in the previous part of the lecture, there's no closed form solution. If we set to 0, we wouldn't be able to complete the closed form solution. So we use the gradient ascent algorithm. So if you remember the previous lecture, we were minimizing the negative of the log likelihood. So we use a gradient descent algorithm. But here we are maximizing instead of minimizing. We are maximizing the log likelihood with respect to w. So here the algorithm will become the gradient ascent algorithm. So the gradient of the function, as you remember, the gradient of a function f of parameter x points in the direction of the steepest ascent of the function. So we start with some parameter and want to update the parameter with in some direction, right? So we can select any of the direction, but we want the direction where we can ensure that the degree of decrease in the function f would be maximum at that particular point in time, and that direction is the gradient. So we get the gradient ascent algorithm. Since you are maximizing, so we'll update the parameters w in the direction of the gradient. So we get gradient ascent algorithm. So now let's see how do we update the parameters w to obtain the optimal solution or the maximum likelihood estimate of the parameters w. So in gradient ascent function, as usual in the gradient descent, we'll update the w as w goes to w plus sum all I equal to 1 to m yi minus 1 over 1 plus e to the power negative of phi of xi transpose times w times phi of xi. Right? So you just write in a more structured manner the gradient ascent algorithm. So we'll just randomly select some w. Randomly select w. Which will denote by just w, right? And until convergence, until some convergence condition is achieved, with the following update. For all the data points, do the following update. So here, instead of if we use this entire data set for updating, for example, if we use this route for updating, then basically if m is very large, for example, m is a billion, then we'll for a single update to the parameter w, we'll have to compute this summation over a billion data points, which may not be practical for gradient descent algorithm. So we'll compute it iteratively based on each of the data samples. So we'll use the iterative computation. So we will denote the previous value of w by w pre, a new value by w new. So w new takes the value, the previous w, w pre, plus alpha times, where alpha is the learning rate, alpha belongs to 0 to 1. Yi minus 1 over 1 plus e to the power negative phi of xi transpose w times phi of xi. And we do this until some convergence condition is achieved. So after doing these continuous updates over all the data points until convergence, we achieve the W star or the optimal W, which is the maximum likelihood estimate of the parameters. So that's it in this lecture for logistic regression. In the TS session, you will learn various kinds of stopping conditions. So basically, we just left it blank over here, what the convergence condition is. But you can go through the TA lectures to know what are different kinds of stopping conditions that we can use to stop this algorithm. So that's all for the logistic regression lecture.